Hello everyone. In the last video, we learned how to solve the polynomial equations. In this video, we will learn how to solve nonlinear equations that are non-polynomial and cannot be solved by any analytical method. For finding the roots of such equations, we use numerical method-based techniques that give us approximate solution. In addition to solving nonlinear equations, numerical methods can also be used in calculus, where they can be used to solve complex integrals and differential equations, to name a few. In this video, we will learn how to use a Newton method to solve a nonlinear equation, which is also one of the most widely used numerical methods for solving nonlinear equations. So let's consider a function f of x that can be plotted on xy scale as shown here, and our goal is to find the solution, that is the point where the curve meets x-axis at y is equal to 0. So and that is shown in the plot with this red dot. So we have to find that. That's our solution. So we can start our algorithm with some kind of initial guess, which is x1 in this case. So our goal is to have a tangent line, and tangent, if you remember from the definition, is a line that meets the curve at only one point. So we have a tangent like this, and if you look closely, this is making a right-angled triangle with the gradient as hypotenuse, and the base is the difference of the new point x2 and x1, and perpendicular is the value of function at our initial guess x1. So how could we compute this point x2? From the gradient definition, we can say that the value of hypotenuse is simply the ratio of perpendicular and base. So we can write something like this. Gradient, that is represented by f prime, or in fact it is a derivative of the function of x, and it is the ratio of f of x1 and a difference of x2 and x1. So if we make this equation the subject of x2, we get the equation written here. x2 is equal to x1 minus f of x1 divided by f prime of x1. So if we see if x2 is our desired solution, so we see that if we trace x2 to y-axis, it's still not at 0. So it means that it is not our solution, and we have to iterate the same process one more time and see if it is at 0, and if it's not, we have to continue. So this is an iterative process. So let's do this step one more time. So now this time we will have our initial point, or the new point, as x2, and we will do the same thing, like we find f of x2 and have a tangent line on that point, and let's see where that tangent intersects x-axis, and come up with a new value of x3, and so on. So it is shown here at this point. You see that it is now x3 closer to origin now, and we can find the value of x3 using the same mechanism that I told you before. So if we see, now this time f of x3 is here, but still it's not at 0, so we have to repeat the step one more time with the new value x4. And with x4, we see that after finding the value of x4 using the same gradient technique, we find a new value x5. And now with the value of x5, now we can see that x5 is somewhat converging at x is equal to 0. Maybe if we zoom this picture, we can see that it's not entirely at 0 or exactly at 0. It is somewhat close to 0. So in Newton Ralphson method or Newton method, we always define some kind of threshold to see whether the solution is approaching or has approached towards the desired solution. So in the MATLAB, if we have to do all kind of iterations by using the for loops, and we have to find derivatives with some kind of symbolic toolbox. We will go through the detailed process in MATLAB in our next video, so do sure to check out our new video whenever it comes. Until then, bye.